We'll now be continuing the discussion on the Kelvin-Helmholtz radial instability, the instability of two superposed streams with different densities and different velocities. Let me quickly recap what we did in the last lecture. So we spent a great deal of time setting up the basic equations and the boundary conditions. So we're doing this problem for an inviscid irrotational fluid. So each of these streams themselves are inviscid and irrotational. So I can define a velocity potential, and the velocity potential, we give them separate labels. For the upper fluid we call it as phi2 and the lower fluid with phi1. Then the fact that the fluid is incompressible basically ensures that the velocity potential satisfies the Laplace equation. That's my equation number 4. And we perturb the interface by the function z is equal to eta of x, y, and t. And on above and below this interface, we have the velocity potential phi1 and phi2. Similarly, we have pressure P1 and P2, densities ρ1 and ρ2, and so on. So we write down the boundary conditions that are relevant. If you go far away from the interface, meaning go off to infinity, then you would recover the uniform free stream in the far field. That's the first condition. Then we had the kinematic condition. And finally, we wrote down the normal stress balance where surface tension gamma also enters the discussion. So we will now continue from where we left off. These equations, equation number 2 to 8, equation number 2 is basically the definition of the fact that there is a potential on both sides, and I'm defining the velocity in terms of a potential, all the way up to equation number 8, which is basically the relationship between the pressures on using the Bernoulli's equation. So that's the normal stress balance. Now all these equations from 2 to 8, they basically pose a nonlinear problem for us. It's these comprise the nonlinear stability problem for the basic flow that we considered. Let me write that down. Equations 2 to 8 pose the nonlinear problem for the instability of the base flow, which we gave the label 1. Let me show you the base flow. The base flow, you can see the numbering 1, that's the base flow. U2, U1 and ρ2, ρ1, and the pressure is also varying linearly with height. So now that we have the equations, now we'll do a linear stability analysis. For linear stability, we first put the phi2, that is basically the velocity potential in the upper fluid, the total velocity potential. This would be u2 times x plus a perturbation. And the perturbation is represented by a prime. Now note that if you do not have a perturbation, the velocity potential is simply u2 times x, because there's only one component of velocity. And for the lower fluid, phi1 would be u1 times x plus phi1 prime. This is for z greater than eta, and this is for z less than eta. This will label it as 9, just continuing the numbering from where I left off. And we also want to say that this is linear. Linear meaning perturbations, the magnitude of these quantities, that is phi2 prime, is much less than 1, and phi1 prime, this magnitude is much smaller than 1. So what does it mean? They are much smaller than 1. It means that I can ignore products of phi1, phi2, eta. These are small. The products between these quantities themselves are small and can be ignored. Only the linear terms will be retained. Any product or a quadratic term or higher order terms will be ignored. Now having defined the expression for phi on both the fluids, we also want to impose one more condition. We also want to say that eta is small and its derivatives are also small. Also small, that is del eta by del x is much smaller than 1, del eta by del y is much smaller than 1, and g times eta is much smaller than u1 square and u2 square. Right? This is what we have. So let me just write this last one again. G times eta is much smaller than u1 square and u2 square. So let's write down the linearized equations. So for your benefit, some of the key equations that we'll be using, I have put them in a box on the side. This is basically this del phi 2 is equal to u2 and del phi 1 is equal to u1 is one of the earlier equations that we had written down. I believe this was the first boundary condition. That's equation number 5, I believe. Yeah, that's equation number 5. So let's write down these perturbation quantities. If you say that del phi of 2 is u2 for the total one, if you substitute equation 9 into this 5, this is basically what we had written down earlier. This was 5 from the what we had done in the last lecture. If you substitute this, we get in the original Laplace equation, I get del square phi 1 prime is equal to 0. This is for z less than 0. And del square phi 2 prime is equal to 0 for z greater than 0. That's the first thing that I get. Right? Now, we'll label this as equation 10. Now, let me mention that here I have put the boundary condition as less than 0 and greater than 0 rather than less than eta. So, in case you are wondering, the idea is the following. The idea is that the boundary conditions for the perturbation quantities all perturbation quantities are applied at z is equal to 0, not at z is equal to eta. The reason for this is, if you calculate the perturbation quantity, let's say phi prime, it could be either phi 1 or phi 2. If you look at the value at z equal to eta, you can do a Taylor series expansion of z is equal to 0 plus eta times del phi by del z at z is equal to 0 and so on. Speaking of the Taylor series expansion, Taylor himself has, I think in the 1750s and 1760s, he had actually worked on problems in capillarity. He had actually done experiments on capillary rise in tubes. So anyway, if you write it down like this, then these quantities are small, because I already said product of perturbations quantities will be ignored. So eta is small, del phi by del eta, the phi is also small, phi prime is also small, therefore product is also small. That's the first thing that we have. Now let's write down the boundary conditions that we have here. So my governing equations are, the Laplace equations as 10. That's my governing equation. The boundary conditions would be the first boundary condition would be del phi 1 prime goes to 0 as z goes to minus infinity. So note that the condition 5 says del phi 1 goes to u1, the total quantity goes to u1 as z goes to minus infinity. If we just simply substitute phi 1 is u1x plus phi 1 prime, then gradient of phi 1 will simply be u1 plus gradient of phi 1 prime. So if we say that as z goes to infinity, or z goes to minus infinity, as z goes to minus infinity, if del phi 1 goes to u1, it means that del phi 1 prime, whatever is left, has to go to 0. That's basically the boundary condition that we are writing down. I'll erase this part. So the first boundary condition is del phi 1 goes to 0 as z goes to minus infinity. Similarly, we have a similar boundary condition for the upper fluid. As z goes to plus infinity, right? This we label it as 11. And finally, we have to write down the kinematic condition. The kinematic condition, for your reference, is also given. This, I believe, was equation number 6 from the previous lecture. I have just put that, a snippet of that. I have put this in the corner so that we can follow this and write it down. So this is the first boundary condition that we have. The second boundary condition, if you notice here, we can notice a few nonlinear terms. If you look at equation 6 on the side, then you notice that del phi 1 by del x would be, let's write that down, del phi 1 by del x times del eta by del x. We have a term like this. What will happen to this term? Now if I say that phi 1 is u1x plus phi 1 prime times del eta by del x, this becomes u1 plus del phi 1 by del x multiplied by del eta by del x. Now clearly these two terms, the product of these two terms will be very, very small. Therefore, what you essentially get is u1 times del eta by del x. That's what you would get. Now similarly, the other term in the boundary condition, which will be del phi 1 by del y times del eta by del y, both are small because this essentially becomes del by del y of u1x plus phi 1 prime times del eta by del y. And so this simply becomes del phi 1 prime by del y, del eta by del y. And this is a very small quantity, right? And therefore, I can basically write down the kinematic condition for the perturbation quantities as follows. only the linear terms will be retained. So I have del phi 1 by del z will simply be del eta by del t plus u1. u1 is the base flow, the uniform stream below the interface, times del eta by del x. Similarly, we have del phi 2 prime by del z will simply be del eta by del t plus u2 del eta by del x. This is my equation number 12. So that's the kinematic boundary condition. It's coming from 6. And finally, we have to write down the normal stress balance. The normal stress balance, again for your benefit, I have put the original normal stress balance term that we had here. This was, I believe, equation number 7 that we have here. 7, or was it 8? Yeah, I think this was related to 7. Let's basically look at this normal stress balance term. Now again, notice that the constants C1 and C2 get cancelled out by the base term and the base flow quantities, because we already have shown that equation 8 essentially says rho 2 C2, rho 2 times C2 minus half U2 square is rho 1 times C1 minus half U1 square. So if I substitute in this equation 7 that I have on the side, if I simply substitute P as, if I write down the phi as phi 2 plus phi 2 prime, the mean flow plus the prime. Similarly, phi 1 as ux plus phi 1 prime. Then if I retain only the linear terms, this is what I get. I get rho 2 times, only I'm retaining the linear terms, u2 times del phi 2 prime by del x. Note that there is a minus sign in the second term. So plus del phi 2 prime by del t plus g times eta. This will be the first term, that is P2. Then I have rho 1 times u1 del phi 1 prime by del x plus prime by del t plus g eta. This will simply be minus gamma times curvature. Now what's the expression for the curvature that we wrote down? If you notice the expression for the curvature that I am just highlighting in a box now for your benefit, there are several terms which are products of perturbations. For example, a term like this. This is the product of eta xx with eta y, so it would be very small. The last term, again, this is also small. And in the denominator, you have eta x square term and eta y square. All these terms that I've highlighted, they are all basically small. And so if I ignore all the terms and only retain the linear terms, then I simply get minus gamma times eta xx plus eta yy. And where will this boundary condition be applied? This will be applied at z is equal to 0. This entire thing that I unfortunately had to write them in 3 separate lines, this is my normal stress balance. So now we have, maybe I think I should label this. Let's call this equation as 13. So now we have the linear equations and the boundary conditions. Equation 10 is the Laplace equation for the perturbation quantities. The perturbation quantities has to satisfy the boundary conditions 11, that's the far field conditions. Then we have condition 12 is the interface condition. This is again 12 is at z equal to 0. This is at z equal to 0. And finally, the normal stress balance is also applied at z equal to 0. And recall that we are doing it at z is equal to 0 because if the perturbation eta, the amplitude of perturbation is small, then I can always Taylor series, I can take a Taylor series expansion of a perturbation quantity about z is equal to 0, and therefore the higher order terms become very small. So the leading order term, which is the perturbation quantity evaluated at z is equal to 0, is what survives. Now what we now have is all the equations, all the above equations have constant coefficients, and the boundaries are homogeneous in x and y directions. So therefore we can use the method of normal modes. For those who may not be familiar with this, I request you to please look at the lecture on Introduction to Linear Stability Analysis that I gave. So that's mandatory for you to be able to follow this discussion. So if we write down the method of normal modes, essentially says that the perturbation eta, which is a function of x, y and t, will simply be some amplitude quantity eta prime times e power I kx plus ly plus st. And similarly, the perturbation quantity phi prime, which is a function of x, y, z and t, will simply be, we'll call it as phi 1 hat. The hat indicates it's also a perturbation quantity. It's an amplitude or an eigenfunction. This is a function of z alone, and in the homogeneous directions I have e power I kx plus ly, and the time dependent is assumed to be exponentially varying. And similarly, if I have for the other last quantity, will simply be phi 2 hat of z st. We'll label this as equation number 14. So it's useful to know that I have exponential of st term. That's the time dependent variation. The dependence of time is like exponential like this. So this says that if the real part of s is greater than 0, then flow is unstable. If a real part of s is less than 0, then flow is stable. And if the real part of s is equal to 0, flow is neutrally stable. Further, when you have the neutral condition, in this condition, so I have three cases here. In this condition, if imaginary part of s is not equal to 0, if it is non-zero, then we can sustain oscillations. So the flow can sustain oscillations forever. It's forever because the real part of s, which is the amplitude variation, how the amplitude grows and decays in time, that part is 0. Therefore, there is no, if you have a perturbation, that perturbation will continue to oscillate forever. That's when the real part of s is equal to 0. We will encounter all these cases. The real part of s less than 0 is actually unphysical. but I will not go into details of why that's unphysical. If a real part of s is less than 0, we'll always get a real part of s greater than 0 as well. That's because my entire equations and the all the linear stability analysis, when I do the equations, they're all basically, we get a linear and a real or ordinary differential equation. So the solutions always will be in complex conjugate pairs. But anyway, those are technicalities that are not, we don't have to go into those details. Now, let's basically look at substituting the linear stability analysis in this. For example, equation 10. What is equation 10 for us? That's the Laplace equation, right? The Laplace equation. The Laplace equation, let's say for 1, let's write it down. Equation 10 gives us del square of phi 1 prime is 0. And what does it mean? It means del square of phi 1 prime by del x square by del square partial derivatives, second derivatives, del square by phi 1 prime by del z square is 0. Now, if phi 1 prime is phi 1 hat of z e power I kx plus ly plus st, I can then say del square by del 1 prime square, second derivative with respect to x, will simply give me minus k square phi 1 hat e power I kx plus ly plus st. This is what I'm going to get. Similarly, del square by del 1 prime by del y square essentially gives me minus L square phi 1 hat e power the exponential term. And finally, del square phi 1 by del z square, this is for the prime, the perturbation. This essentially gives me d square phi 1 hat by dz square. This is the total derivative multiplied by exponential of ikx plus ily plus st. This is what I have. So if I substitute all these three things into the Laplacian, so let's basically move this aside a little bit so that we can do it right here itself. If we substitute all these three things into the above Laplacian, what we now get is minus k square of phi 1 hat minus L square of phi 1 hat plus d square phi 1 hat by dz square is 0. The exponential term I'm not writing because anyway it's not going to be 0, and therefore I simply get d square by dz square minus a quantity called m square of phi 1 hat is 0, where m square is k square plus L square. That's my first relation that I've got. And similarly, so I can now write equation 10 becomes d square by dz square minus m square of phi 1 hat is 0, d square by dz square minus m square of phi 2 hat is also 0. Both are basically evaluated at z is equal to 0. This is for the fluid above and for the fluid below. This is for, sorry, I made a mistake here. This is for z greater than 0 and this is for z less than 0 and z greater than 0. Now, we can look at this equation that we have here and simply substitute the simple exponential form. So if I have d square by dz square minus m square of phi 1 is equal to 0, we can say, to solve this, we can assume phi 1 of z to simply be of the form e power lambda z, where lambda is unknown. If we substitute it, I simply get the relation lambda square minus m square is 0, and therefore I get lambda is plus or minus m. Therefore, the two fundamental solutions, it's a second order equation. The two fundamental solutions for phi 1 prime, or sorry, phi 1 hat will simply be sum a1 into e power m z plus b1 e power minus mz, right? Now, if we say if phi 1 hat, sorry, if phi 1 prime well, let me put it this way. If we use boundary conditions at infinity, so what was the boundary condition in infinity? It says that as you go far away from the interface, the perturbation quantities have to disappear. Now, in this case, phi 1 is valid below the interface. My interface is basically like this, and this is basically region 1 and this is region 2. So as you go far away from the interface to minus infinity, you cannot have this quantity growing. Phi 1 cannot be growing. Therefore, we have to substitute, we have to suppress b1. So b1 essentially has to be 0, right? So only the decaying terms will be considered. That's also consistent with what we had said, that the perturbation is basically confined to a region closer to the interface that is deformed. Far away from this perturbation, you would expect the perturbation amplitude to decay to 0. Therefore, I simply have phi 1 prime would simply be a1 e power mz. Similarly, phi 2 prime would simply be some a2 e power minus mz. Remember, for fluid above, as z increases, e power minus mz decays. This ensures that we are basically not having growing terms as you go to infinity. So we label this. So the general solution that we had got, let me quickly recall. So this is our general solution, and then we label this as 16 and 17. That's what we have now. Now, let's quickly see what we have got so far. If you look at equation number 12, it's a simple relationship between phi 1 prime and eta. And equation 13 is also a relationship between phi eta and the base state quantities, that such as density, velocity, and we have the interface quantity gamma, right? Now, equations 12 and 13 give us three homogeneous linear algebraic equations. Remember, they have three of them. So at 12 we have two equations, and the 13th is the third equation. We have three equations. These are all these equations are coupled to each other. Three linear algebraic equations for the three unknowns. What are the unknowns in the problem? They are basically eta hat. Now for phi1, the unknown is a1 and the other unknown is a2 for phi2. Now the idea is, some of you, if you are wondering, what about m? Is m not an unknown? The idea is m is not an unknown. We don't treat m as an unknown. The idea is, if you recall the stability analysis that we've done for the previous problem, when we assume a normal mode form that is shown in equation 14, the idea is we want to get a dispersion relation. The ultimate goal is to derive a dispersion relation. What is a dispersion relation? It tells you how S, the growth rate, S, complex growth rate, it depends on the wave numbers K and L. K and L are the wave numbers. So the idea is that once you have the dependence, as a user, you can specify the wave numbers K and L, which means that that's not an unknown. You can specify it and ask what is the value of S that I get. And once I get the value of S, if I'm able to determine the value of S, the three conditions that I have here, that is whether the real part of S is greater than 0, less than 0 or equal to 0, this tells us something about the stability of the problem. Now let's basically, we have three equations for three unknowns. Let's quickly do the analysis using equation 12. Equation 12, it basically gives us, what was equation 12 for us? Del phi 1 by del z is equal to del eta by del z, del t, plus u1 del eta by del x. So we have del phi 1 by del z, that is m times a1 e power mz. I'm not writing down the exponential term because the exponential term, that is exponential of I power I times kx plus ly plus st, will cancel out on both sides. The right hand side is del eta by del t, that is s times eta hat, and I have u1 times del eta by del x, that is ik eta hat, and this essentially gives me a1 in terms of the other parameters, s plus ik u1 times eta hat by m. Similarly, if I do the use equation number 13, I get a2 will be minus of s plus ik u2 eta hat by m. So let's call this as equation number 18. So now what we have got is we've used two of the equations, 12 and 13, to get these constants a1 and a2. These are the amplitude terms a1 and a2 in 16 and 17. Now what we want to do is substitute. Now once we know a1 and a2, I basically know phi1 hat and phi2 hat. And if I look at equation number 18, equation number 13, I can simply substitute phi1 hat and phi2 hat into this equation and the expression for eta and derive the dispersion relation. So let me quickly summarize what we have seen in the lecture today. We started off from where we left off in the previous lecture. That is, in the previous lecture we derived the base state quantities and the perturbations. Then base state quantities for the full nonlinear problem. The full equations were there for the nonlinear stability. Now we perturb all the quantities because we're perturbing the interface. So therefore there is a similar perturbation for the velocity field. Phi1 and phi2 are basically the perturbations to the velocity potential. Phi1 prime and phi2 prime are the perturbation quantities and they are small. That's the first thing. So therefore we are in the linear regime. We just substituted the perturbations into our original equations, that is from equation 2 to 8, and we derived the linearized equations. Equation 10 basically is the governing equation. 11, 12, 13 and 14 are the 11, 12 and 13 are basically the boundary conditions. Now to proceed further, what we did was we assumed a normal mode form for the perturbations. We substituted the normal mode form, and at this point we basically managed to get the constants A1 and A2. In the next lecture, we still haven't used one boundary condition, which is the normal stress boundary condition. So in the next lecture, what we'll do is we'll substitute all the all the known quantities that we have in the normal stress boundary condition, and eliminate the last final unknown. What is the last final unknown? Eta hat. So right now I've got A1 and A2 in terms of eta hat, but eta hat itself is unknown. We'll substitute into the equation number, I believe 13, that's the normal stress condition, and get the dispersion relation. So I'll stop here and I'll see you around the next lecture. Thank you.